Hi everyone, this screencast is about the loci of complex numbers, and in this first instalment we're going to be looking at situations like this that involve the modulus of two complex numbers. Now there's a couple of ways to look at this. The first way is we take a geometric perspective. So I'm going to write this as z, and then I'm going to subtract. I want to write it as a negative, so it would be minus, sorry about that, this touch screen's getting a little bit sensitive, so we're going to have minus 2, and then we'll have plus I, and the next one will be negative 3 minus I. So if we look at it like this, z is our arbitrary complex number, could be anywhere in the plane, and we're looking at the difference between z and this other point here. So to draw a quick Argand diagram, the point negative 2, 1 would be here, and the point negative 3, negative 1 would be down here. And we're looking for an arbitrary point. Let's think first for the equality. A point which is an equal distance from these two could be right in the very centre. So I might just change my pen colour here. Did that work? I hope. A point that's equal distance from these two could be right in the centre. Equally, it could be off to the side a little bit, but an equal distance, or it could be off to the side a bit here. In fact, what we're talking about here is a perpendicular bisector. So imagine a line between these 2 points and a line that's perpendicular and halfway between. Now for the inequality part. We want the distance to our point from here is less. So this point was the one down here. And to be closer to this point, we would need to be shading underneath. So that's the geometric perspective. But if you had to justify this answer, you'd probably want to have a little bit of algebra to back you up on that one. So here comes the algebra. Now remember, in all of these scenarios, we're imagining that our complex number z is x plus y times I. So I'll write that in. X plus yi plus 2 minus I. So the mod of that is greater than x plus yi plus 3 plus I. So the real part here is x plus 2. The imaginary part is y take 1. That's still the modulus. The real part here is x plus 3. The imaginary part here is y plus 1. And we're still the modulus. So the mod is, of course, x plus 2 squared plus y take 1 squared, all to the power of a half. Then we have over this side x plus 3 squared, y plus 1 squared, all to the power of a half. Now if we were to square both sides, the powers of a half would disappear. Then I could expand out these brackets which are here. So x squared plus 4x plus 4 plus y squared minus 2y plus 1 is greater or equal to x squared plus 6x plus 9 plus y squared plus 2y plus 1. So, come on, pen, change to red. I think it worked. So subtracting x squared from both sides, subtracting y squared from both sides. I suppose while I've got the red pen out here, I could imagine that I squared both of those expressions at the previous step. Now what am I left with here? I have 4x and I have 6x. By transposing, I'd have negative 2x. Then negative 2y plus 2y. Transpose this term, and I'd end up with negative 4y is greater or less equal to. Now let's see, what have we got there? 9 plus 1 is 10 over on the right. Subtract 4 is 6. Subtract that 1 is 5. That's greater than equal to 5. So that's an inequality. That's an expression that I could use. How do I sketch this? Well, let's look. So real, imaginary. Now let's just imagine here, if x equals 0, well, if x was 0, then this term would be nothing, and we'd simply divide by minus 4. Y would be 5 divided by minus 4, so negative 5 over 4. The y-intercept is, there's negative 1, there's negative, y-intercept about there, negative 1 1/4. If y was 0, then we'd just have 5 divided by negative 2. And so on the x-axis, our intercept is down here. So this is the line joining, it's an equality, so it'll be a solid line, not a dotted line, so try to draw that through. Now, how do I decide which side of the line to shade in? Well, the easiest way is to pick a spot on the Argand diagram and substitute. I'm going to pick the spot 0, 0. If I substitute 0, 0, I end up with 0 is larger than 5. That's not true, which means that that spot is not part of the region that I need to shade. Therefore, I should be shading the other side of this line. Now that matches what we had thought geometrically. So we've got a geometrical way of thinking. When would I use this? Well, if the question was only worth 1 mark and it just expected me to show the picture, I would do that. If it was worth more than 1 mark and I therefore expect to have some working, I would show the algebra and I would get to this point here. Now, let's just go and have a quick look at GeoGebra. I've marked in the 2 points that we were dealing with. So, geometrically, I could, that's not the right place. Geometrically, I could ask for a perpendicular bisector between those 2 points, and there's that line. Isn't that lovely? Now, the thing with GeoGebra, that's just going to give me a line and not a whole region, so I might take that away, and instead, I will enter that expression that I had on the previous screen. So it was, I've got to figure out how to use this little keyboard down here now. That's interesting. Where are my numbers? Nope, they're not there. Oh, there it is. I just have to press that. So I needed negative 2, back to the keyboard, x, sorry, it's a bit slow this, isn't it? Minus 4y. Now hopefully I've got some mathematical symbols there somewhere. Not there. There it is. Greater than or equal to 5. And hit enter. And there it is. So I've got the solid line, which is the perpendicular bisector running along here, and GeoGebra understands with the inequality to shade the appropriate side. And so that matches exactly what we thought when we were back here looking at OneNote. There's the locus of, why can't that scroll? There it is. There is the locus of this expression. That's enough for now. There'll be more installments using other forms of loci coming soon.